So we're looking at how do we identify cylinders that have potentially got a compression issue just from relative compression waveforms alone. So that's the idea of what we're doing today. So to start with, we're obviously going to need to download the software, so PicoScope Automotive. So to go to there, you'd need to visit our website, which is picoauto.com, and then find the downloads page. When you do the download, you'll actually have two bits of software that are automatically installed at the same time. You'll have PicoScope 6 Automotive and PicoDiagnostics. Now, some people, to be honest with you, a lot of people that we speak to never really sort of use PicoDiagnostics to its full potential. And hopefully after today, you'll see how simple and non-intrusive it is to actually get some really useful information from it. So as I said, the idea being non-intrusive. So the two that we're actually going to look at, you'll see there's a number of different options when you open the program. The two that we're going to be mostly focusing on today are the battery starting and charging and the compression test. Okay, so onto the connection. So we'll start with the battery starting and charging and how to connect. So it's very, very simple and straightforward. All we're going to be doing is taking our PicoScope and we're going to connect our ×1 test lead, and we're going to connect the signal wire to the battery positive and the black signal ground to negative, and we're going to use our 2000 amp current clamp around the battery positive or negative, which is easiest to get to. So we're just going to move to another camera. So then we should be able to have an overview of what we're doing. So there we go. Right, so I can stop now. So Barney, we should still be just have me on the camera now. Is that correct? Yeah, perfect. Right, okay. So if we move across, so we have our scope already connected to our computer. So if we look at the battery, we have a ×1 test lead. We're going to take our signal lead onto battery positive and our signal ground, or our ground lead, onto battery negative. That will then be connected into channel A and then the current clamp. So you'll see from the current clamp itself, we have two different options. So we have 200 amps and 2000 amps. For this test, we are wanting to be on the 2000 amp range. Now you should see that we have, we'll just wait for that. That's breakfast van coming through, perfect. So yeah, so as we were saying, so the 2000 amp current clamp will have the battery on light. Now this clamp actually has a function where it will automatically turn off. So to prevent that from happening, we can actually turn the clamp off, press and hold the 0 button and turn on. Now we have the red light on. Now that means the clamp will stay on permanently until the battery runs out. For the purposes of the test today, we're going to leave it on because I don't really want it going flat or turning itself off halfway through. So we're going to use the battery negative to clamp the current clamp round. We can see on the arrow on the current clamp, if you can get in there, Steve, and see that. You should see the current clamp arrow there. For the battery negative, obviously current's flowing back to the battery, so we can point the arrow towards that point. If it was on the positive side, then the arrow points away. Current clamp, then on channel B. And that's it, that's our setup done. So what we can do now is I will come back to this camera. We will reshare the screen, and we are actually going to look at the PicoDiagnostics program. So when you open PicoDiagnostics for the first time, this is the screen that you're likely to see. So as I said before, we have a number of different tests on the left-hand side. As I said before, the two that we are mainly interested in are the battery test and the compression test. So we'll start with the battery test. here we have some information to fill out. Now, if you're still not entirely sure about the setup, we can go to Contents, we can go to Tests, we're looking at battery test, and under here we've actually got some more information about how to connect. So if you're ever unsure, this is obviously how we can find and get a little bit of extra help. So a few bits of information to fill out down the bottom here. So we have a 12-volt battery. It's a lead acid on this vehicle. Temperature, be aware of it. Obviously, it's the battery temperature itself. In our workshop at the moment, it's quite a nice, comfortable 20 degrees. However, if the outside temperature when you're doing this test is freezing cold, then obviously bear in mind that we're going to need to allow for that factor. Cold cranking amps on this battery is 760. You can usually find it on the top of the battery. If not, there's a number of good battery websites out there now that will give you that recommendation as well. This is a EN standard. So with everything set up, all we need to do now is start. I'll run around and start the engine. So as we can see from the results down below, we have our raw data that's captured at the top of the screen. We then have our battery condition, so our initial voltage being 12.7, so that gives us 100% state of charge. This battery is fully charged, and it's something we made sure of last night, but in the event of making sure that with the rest of the tests, making sure that you've got your battery charged is going to be important, as we'll see later on. So I'm happy that this battery is good, so I can move on to the next tests. So, just want to move back to the presentation. So that's the connection done. Oh, there we go. So as I said before, the results are, as we can see here, and we can just zoom in at that point and see a little bit more information. Making sure that you've got a good battery and good charging system is one of the very first things that you do in your vehicle health checks. That's quite a nice, easy, important one. And with this result, we can also print this off and give to the customer. So quite a nice, useful tool to prove that you've done something, but not without having the need to buy expensive battery test equipment. So the next test, we're going to be looking at the red seat compression test. Now for this test, it's even more simple than the original battery test. So all we're going to need is one test lead, which goes across the battery, as we can see there. We do need to be mindful that we need to make sure the engine can't start. So we need to prevent the engine from starting, and obviously ensure the battery can support 6 seconds of continuous cranking. As I said before, the reason why we do the battery test first is obviously to make sure that the battery is capable of cranking the engine for that period of time. Important thing again to mention there is prevent the engine from starting. So to stop a diesel engine from actually starting up, there's a number of different ways. We can disconnect the injectors, take away the fuel pump, crank sensor, or just completely removing the fuel supply altogether will result in the vehicle not starting. So picking the most accessible is usually the quickest option. Normally the injectors themselves can be just removed quickly. So if we just now come back over to the vehicle and how we're going to do the setup. So as I said before, we don't need the current clamp now anymore. So we can remove this from our setup. And all we're going to be doing is just using a simple test lead across the battery, and it's only battery voltage that we're interested in at this point. This makes it a very simple and very quick and easy test. Okay. There we go. Right, perfect. We should be back up now. crossed. Said to be patient. We will do this live as well, but the original test results that you'll see, if you have a compression issue on an engine, you are likely to see something like this. Now, the actual results, we can actually look at the raw data and what we've captured. So we can see from here that we have a big voltage drop across the battery when, sorry guys, I'll just bear with us just while that catches up. There we go. I think you should all now have the raw data and the compression results on the screen together. Fingers crossed. So we can see that from the initial voltage drop when the engine begins to crank. And then we have this repeating sawtooth pattern that occurs afterwards. What the software will do is it will look for the lowest voltage drop and determine that that is the highest performing cylinder or the best performing cylinder in terms of compression. Now, we try and understand how relative compression works. What the software is doing, what the vehicle is doing, is during cranking, the piston's coming up to compression. So naturally, the starter motor needs to draw more current and more from the battery in order to overcome that restriction during compression. Where the battery then voltage drops lowest, that's that best performing cylinder. If we have a cylinder that's doesn't have as much compression on it, the starter motor doesn't need to actually have as much current in order to overcome that restriction. Hence why we have that drop of that 59%. In that instance is where we have a poor performing compression. So we're going to do this live as well so we can see exactly what's going on. So if we just come back to the webcam just for a second. So it should just be on the screen. Hopefully anyway, that's the idea. Oh, I need to switch the camera. There we go. There we go, lovely. So we come back into the engine bay. Now what we're going to do in order to prevent this vehicle from starting, we actually have a nice easy fuse, which is just down under here. And this fuse here is one that actually provides the power supply for the inlet metering valve. So if we remove that on this vehicle, the inlet metering valve removed, it will no longer start. So we can perform our relative compression test very easily, not actually having to go anywhere near the injectors. It's very simple. Okay. Can go back to our PicoDiagnostics program. And to do that, so now we're going to click on compression test. So it will ask you if you wanted to save any data. If it's something that if it's a customer's vehicle and you want to collect all your evidence, make sure you keep it saved. So for us, just to fill out on this point is we need to tell it how many cylinders it's got, make the connection across the battery and press start. Ensure the throttle is held open fully open during this test. That's fine. Okay, and if we could crank the engine, please.
We're not seeing the software on the presentation. Can we share those?
Yeah, it should be shared. Yeah. I don't know if you can hear it, but there is actually a distinctive difference in the engine sound as well whilst we're turning over. But we can see from the results straight away that we actually have a cylinder down on compression. Again, we can look at the raw data. You can see from there it looks quite fuzzy, which is fine. The software allows for that and will actually help filter that up. So we can see now that we've got this potential drop. Let's see if I can find a slightly better view for that. So there we go. So we have a drop, a drop, a drop, and then not so much of a drop. Now this is the cylinder that we're interested in. As it appears, we have a poor compression. So the whole purpose of this this presentation, then I guess, in this webinar, is how can we actually determine what cylinder that is. So now, if we should just be able to do that. Still waiting for the next screen. There we go. So, just gonna wait for that. Sorry guys, a few internet issues I think at this point. Making the program a little bit slower. There we go. So it should now have, you should now have, can we identify the cylinder? If we don't have a WPS 500X, now, why wouldn't we have one? I'm not entirely sure, but but if you don't have one, we can still very much do this test. And obviously it's about understanding the possibilities with Pico and how you can use the equipment to its full effect. So yes, we can identify that cylinder, but we will need to now go into the PicoScope 6 automotive software. Now, this will allow us to manually set up the software and make use of all 4 channels if we're using a 4-channel scope. Now, don't be deterred though, guys. If you've only got a 2-channel scope, we can still very much do all this testing, and I'll show you about how we can actually use it to its full advantage as well. So, setting the scope up manually for relative compression. Now, if we've never seen this screen before and we've not sort of been, we're new to oscilloscopes, something to get into the mindset about how we do this. So don't be afraid. Connecting the scope up to a vehicle is no different to how we would use a multimeter. All we're introducing now is a time factor. So the screen that you're presented with is formed up of a grid. Now this grid is split up, as you can see, into a number of different ways, and we now have things called divisions. Across the screen you should be able to count that there's 10 divisions, and the voltage axis for whatever range or whatever accessory we're using is now in the vertical axis. Right, okay. So taking your first measurement. So we can set the scope up to capture any signal automatically. There's a couple of things to remember, and it's very much up to you, but I like to try and remember what probe it is I'm using, what the range is, how much time do I need across the screen, do I need a trigger? So our first thing, which displays, there we go. Hopefully now guys you should have the slide with probe setting on the screen. So selecting the current probe, the correct probe is essential to a good capture. There's no point looking at battery voltage when you've got a current clamp set up. It will be in completely the wrong scale. So make sure that we're selecting current probe if we're measuring current. Now for the next bits of the test, we'll come back to that. We'll come back to that as we move forward. So we'll do this live as well, and I will set this up live within the software. So you'll see you'll be able to click on channel A. It will give you a drop down, and where it says ×1, which is our current default, which is our signal test, which is our ×1 test lead, you now be able to click on that box, and it will bring up a number of different options for you to select. So the next bit to be aware of is the range setting. So again, no different to your multimeter. It's just a matter of, instead of twisting the dial in order to select whether you're looking at current or voltage, we just need to make sure that we're selecting a range that's good for our measurement. So if we're looking at battery voltage, then make sure that you allow for ±20 volts. You could just leave it on auto and it will automatically do it for you if you wasn't sure. But also then make sure if you're looking at current that you got the highest one. If you're looking at maybe injectors, then go for your highest one first, and then step down if it looks like it's too far out. And onto trigger setting. Now, whether or not you want to put that in, they do help stabilize your waveform on the screen. Triggers when you set a trigger, it has to meet certain specifications that you put. So the waveform has to cross certain points for it to actually be stabilized on the screen. One of the things we would always advise here, if you're not used to using triggers, is to use the auto trigger. Now, what that will do is it will wait for a certain period of time. If the trigger isn't met, then it will carry on. Using the other settings, which are repeat and single, if the capture doesn't, or the waveform doesn't pass through the specific conditions that have been set, you won't have anything happen on the screen. It won't work. So as long as we want to make sure that we've got something on the screen, I suggest just using the auto button to begin with. Another important factor here to mention is our sample rate. I'm just going to wait for that slide to load. Typically for automotive use, we found that 1 million samples is more than enough for what we need to do and gives us good detail, especially when zooming in. So stick to 1 million samples. Okay, so what we're going to do now then, guys, is we will do the setup and we'll do a capture as we did with our PicoDiagnostics software, but this time we're going to do it in PicoScope 6. Now, you'll notice I put on there about the initial results. I'm going to use a current clamp for this setup, only because it's easier to associate a peak in current as a compression event. So, as we said before, pistons coming up on compression will naturally draw more current, or the starter motor will draw more current in order to keep the engine rotating. So it's just a bit more of a visual thing than anything else. There'd be no reason to not use voltage if you're more comfortable using that. So let's just now then, if we just go quickly back to our camera, and we'll just show you the setup from that point of view. There we go. So again, we're going to use the same idea before. We're going to prevent the engine from starting. So we've still got the fuse removed for the inlet metering valve. Now instead of instead of voltage, we're going to just take the test lead off, and we're just going to use the current clamp on channel. So current clamp back on again. We'll put it into staying on all the time, permanently on. Again, round the negative lead. And onto channel A. Okay, lovely. So, now guys, now this is the main PicoScope 6 automotive software. You can do all of this, you can download the software for free, and you can play about with this software in demo mode. There's no need to have a scope connected at this point. If you wanted to just have a little play, have a little look at some of the other files, if people have sent other files in as well, so there's nothing to stop you just using the software, getting to grips to it, having a go and seeing where all the different things are, and obviously when you're good and ready, then get your scope connected and then go from there. So the setup, as I said before, what we can do is we can look at the probe. We're going to need to change this now to a current clamp. So if you scroll down here, then you get to the automotive, you can see the 2000 amp current clamp, and it's in 2000 amp mode. Now I'm going to leave that on the highest range at 2000 amps. Time-wise, now as I said, this is something that's new when we're looking, if we're just introduction to oscilloscope diagnosis. For this test, for cranking test, we obviously want to be, we want an extended crank. If we remember that the grid is split up into 10, if I did 1 second per division, that now gives me 10 seconds across the screen, which is more than enough to perform a relative compression test. Now I'm also going to put a trigger on. I'm going to put this in repeat, but actually we'll show it in auto first as well, so you can see what's going on. So I'm going to go auto, channel A, in a rising direction, because current is going to go up. Now I can either pick the diamond up at this point and move it about to wherever I want, or I can set it up on here. So I can go 300 amps at 10%. Now, as you can see, just before the trigger, just before the waveform actually comes up to that trigger point, it stops for a second and then continues. When we're saying about using auto in the beginning, it doesn't matter if your trigger doesn't meet those, or if your waveform doesn't meet the trigger requirements, because it will still capture something on the screen. For what we're going to do today though, I'm going to put this onto repeat, and you should see now that that trigger or that waveform does not pass that diamond until we've met the specifications which we've set, which it needs to be 300 amps. It needs to see 300 amps in a rising direction, and that's when I want the software to start capturing data. So, Barney, yeah, if we can crank the vehicle. Thank you. So there we go, guys. So I can skip back, and there we have it. That is our relative compression waveform from PicoDiagnostics, but now in PicoScope 6 Automotive. Within here, obviously, we've got a number of different tools. So we can zoom in on certain parts of the capture. And you can see here also that we've got these rulers on the side. So I can bring these down and start actually making measurements should I need to. All I'm interested in at the moment, though, is this drop, this oddity or this anomaly within our waveform capture, where we have 3 very good peaks and then 1 not very good. So this is the one that we're going to focus on. This is the one that's reported in PicoDiagnostics as a cylinder down on compression. So now, well, how do we identify what cylinder that is? So, determining cylinder 1. Wait for that to come on. It should be there in a second. There we go. So, when identifying cylinders, we normally use an ignition or injection event for cylinder 1, and then use the appropriate firing order to determine the rest. So as before, to carry that relative compression test, we have to prevent the engine from starting. But disabling the engine from a common rail diesel removes the injector signals. So how would we actually determine which cylinder it is? How do we get our reference for cylinder 1? How would we start to do that? One of the things we can do is start thinking about constant signals. So when the engine's rotating, what else is rotating as well? And one of the things that comes into mind is obviously the camshaft. So if we could use the camshaft position sensor, which is used by the ECM to obviously determine cylinder identification, then we can do the same. So by running the engine and viewing the crankshaft position signal with cylinder 1 injector, we can then actually see the relationship between the two. And then after that, then once we know the relationship between the two, if the injector signal is no longer present, we can then run our relative compression test with our camshaft position signal and then actually determine which one was cylinder 1. Some points here then, guys, we do need to be mindful as well of timing. So it may be that cam crank timing may be out. What if the engines come in and or vehicles come in and the timing is shifted? So actually, we've got valve, or the compression issue is due to valve damage, no longer holding compression. If that's the case, then we need to be mindful of that going forward as well. But we'll look at something called the Waveform library if we're not already aware of it, and how we can use the Waveform library to determine cam crank timing going forward, and making sure that the engine mechanically is okay as well. So, should we get to the next one? Right, okay, so let's do the setup then, guys. Okay, so this test then, so we're going to keep our relative compression test on channel A. We now want to introduce cylinder 1 for our reference. Now, the best way to determine cylinder 1 injectors is using the current clamp. Now, this is a great little clamp, gets in nice and easy, plus it's non-intrusive as well, so we're not having to disturb any of the wiring. In this instance, we have actually put a breakout lead on cylinder 1 injector, only because it's actually trapped underneath part of the inlet manifold. So bear that in mind as well when we're obviously looking to get our reference. You don't have to use cylinder 1. You could, if you know, if it's easier to get to cylinder 4, why not use cylinder 4? Just bear in mind that when you're looking at it, that you know that that's cylinder 4, and then put your firing order according to that. So for us, we are going. We can get in there. Let's just shed a little light on the situation, so you can see the breakout lead that we've got there for cylinder 1 injector. Oh, drop the torch. Current clamp onto the breakout lead, 0 the clamp once we're in position, and then put this on channel B. Then we need to place our camshaft position signal onto channel C. Signal to ground, and then our signal lead onto the output. Again, guys, we already have these set up for training purposes, and the van was used on the roadshow. If any of you guys got to come and see that this year. So all of these leads are already made up and broken into. Breakout leads do make things a lot easier, but if you can't use breakout leads, then do what we need to do. Great. So I guess then, guys, there's nothing more to it, but let's take a capture of what we've got there. So the important thing here to remember is that the engine needs to be running. We need to see the relationship between cylinder 1 and the camshaft position sensor. So we need to refit our fuse. And then restart our software. So what we'll do now is we will come back to the software, PicoScope 6. There we go. We should now have that on the screen, guys. Move that back to here. Okay. Now we obviously need to make some amendments now as well. So we need to tell the software that on channel B, we now have a 60/20 current clamp. So channel B, probe, and then this is in the 20 amp mode, so we can click 60 amp, 20 amp. Now, interestingly, guys, this vehicle has got piezo injectors on it. Now, for this purpose, it's absolutely fine to use this version of current clamp. It's not a problem. But you can see there that the range goes from -5 to 20 amps. Not so much of a problem, like I said, for the purposes of this test. However, if you're looking at piezo injectors with the current clamp, it's better or sometimes easier to switch to the 30 amp current clamp. Now, the relationship between the current clamp and how it outputs it as a voltage is exactly the same with the 30 amp as it is with the 2060s. There's no problems in terms of amplitude or anything like that, or the scaling factor between these two clamps. But what it does mean is that when we look at the range, we have now ±20 or ±30. So we can go ±20 amps, and we'll get the full effect of the piezo waveform, or the current waveform from a piezo injector. Channel C is going to be our camshaft position sensor. So on probe, it's just a ×1 test lead. Now, I'm not entirely sure of the range at the moment. If it's Hall effect, they're typically 5 volt. However, if you don't know, go above. Now, this is a 12 volt vehicle, so most things are going to be ±20 volts. Doesn't matter if it isn't for the minute, but we can just go bigger and then rescale later on if we need to, or redo the test again. A couple of extra bits now, guys, in the automotive software that are different to, especially if anybody's using the test and measurement software. This is one of the key differences if you unfortunately downloaded the incorrect version. We actually have the option to put channel labels in, which are really useful when you're doing post-capture analysis, because you might have spent the day collecting maybe 20, 30 captures on a vehicle. I know it sounds excessive, but it has happened to me. And then actually not going back through it, not realizing what on earth everything is. So from here, we can actually do, you can just start typing. So we've got starter motor current. That's fine for channel A. Channel B is going to be injector. So injector current. And then channel C is going to be our camshaft. I'm not sure what camshaft sensor it is at the moment. I'm going to go Hall effect. And then for injector current, I'm going to put a comment there, which is cylinder 1. Okay, so setup wise, I'm happy. Trigger, I'll keep the same because I know my current's going to peak above there as I start the vehicle. So I can leave my trigger in place and we are good to go. If we can start the vehicle then, please, Bonnie. Excellent. Perfect. That's lovely. Okay, so now let's look at this relationship between the camshaft and injector signal then, shall we? So we can use our zoom tool again. Up here, we've got our zooming tool. Again, we can go in a closer still if we would like to. So as you can see now then, we have cylinder 1 injector signal, and then it repeats again. We can use our rotation rulers now to actually mark out where the other events would theoretically be, or the other injection events for the other cylinders would theoretically be. So bringing out the rotation rulers from the right-hand side, we now have the option to use partitions, so we can split the segments up between there and roughly work out where the other cylinders would be in relation to this. So we'd have cylinder 1 here. We know that's cylinder 1 because we've put our current clamp on it. 3, 4, and 2 using our firing order. Now, if we can see here, guys, that there is a definite relationship between cylinder 1 and this falling edge on this part of the camshaft sensor. Now we can scroll along now, so we just move along to the next pattern. So you can see every time that we have an ignition injection event, it is on this falling edge. It's repeatable. It's revealing this pattern to us. So this falling edge in front of this small pulse is giving me the indication that that is where cylinder 1, I can use that as an identifier. So, oh, hang on. There we go. Okay, guys, we'll just wait for the presentation to come back up. Should just move on a little bit more. That's how we said about revealing the pattern and using the zoom tools. And here we have what we've just seen on what we've just captured live. So as I said before, this is where we're looking at that falling edge. And then we have cylinder 1 and cylinder 3, 4, and 2. So as I said, these are the theoretical positions of when them other following injectors or injection events will take place. Now, as we said before, disabling the engine during doing a relative compression test, we are going to lose that injection signal. Ways of actually keeping an idea of where it is. I know we've all sort of seen where that injection event takes place in relationship to the camshaft position sensor on that falling edge before the pulse, before the small pulse. But we can also use reference waveforms to actually keep that image up on the screen for us. So I tell you what, let's just do this live. We might as well. If we come back to this screen here, I'm going to zoom out. I'm going to get rid of them rulers. Now, one of the easiest and the quickest ways of doing this is we can right-click on the screen, anywhere in the grid. It's absolutely fine. And you'll see there's an option for reference waveforms. So from here, we can, any active channel, we can make a direct copy of whatever we have on the screen at the time. So I want to be able to keep channel B and channel C. And you'll see behind there, if I go forward in a buffer, you'll see how they're still there. They're dropped in behind. Slightly fainter, however, they are still there for us to use and call upon for when we do this next capture. So if I now start the scope again, you'll see the captures are still there. What we'll also do now is we will disable the engine. So I'm going to take that fuse out for the inlet metering valve. And we're going to crank the engine. Thank you. Okay. So as we can see now, we have our current clamp still around the negative cable, given now we're back to relative compression. We can see also here, guys, that we now have live data from the cylinder 1 current clamp, and there's nothing on it. There's no signal there at all. However, we do still have a camshaft position sensor. So we know from earlier, and we can obviously call upon this as well if we need to, that our relationship between ignition from cylinder 1 and injection from cylinder 1 was on this falling edge in front of the small pulse. So what we can do is we can bring our rotation rulers out, mark it on that falling edge, and then place it also on the preceding falling edge in that pattern. And now we have a relationship here. So if we remember rightly before, guys, this would be cylinder 1, 3, 4, 2, back to cylinder 1. These peaks indicate a compression event. We know this from our relative compression test. So we have a peak for cylinder 1, another peak for cylinder 3, and a smaller peak for cylinder 4. So have we now not gathered that our compression issue and identified that the issue is on now cylinder 4 because it's not pulling as much current? So there we have it. So in the crux of it all there, guys, we need to reveal the pattern to then determine the relationship between the camshaft position sensor and injection event from cylinder 1 running, and then putting it back into our relative compression test using the current clamp, and we have that relationship. So, lost my cursor. There it is. So just to highlight that a little bit more there, guys. So as we said before, if we're looking at the pattern, we've obviously got the reference waveform there as well. Oh, what's going on there? Technology, it's great when it's working, isn't it? There it is. So we have the peak on cylinder 1, 3, 4, and 2. Now this is from a known good vehicle, guys, so it's not quite the same. So we've obviously got a known good vehicle here, but the pattern is still the same. We're looking for this falling edge from our original running capture. Yeah, so I know this is from a known good one, but it's just an idea of trying to focus in on the patterns that are the relationships between the two, and then obviously coming back to where we've got our low one. So we can go back to back to here, and it should make a little bit more sense where we've got the two. We've got the low compression. Excellent. Right. Okay. So guys, that's pretty much that part of it. I hope that makes a little bit of sense. It's, I say straightforward, I guess nothing's simple, is it, ever? Including doing this. But I like to think that's, that does help, you know, if you're looking at from a relative compression point of view, and you know, if you haven't got a WPS 500, then you still can actually identify cylinders that are down on compression by using these techniques. I guess one thing we was going to mention was the waveform library, wasn't it? And how do we actually find a known good version, or making sure that we have good cam, crank, and ignition signals from vehicles? If people haven't seen this before, then we need to make sure that we have the scope connected. You have to have an automotive scope using the automotive software in order for us to gain access to the waveform library. We do also need to have internet connection, and we also need to have a login for the forum. Now, to get to the waveform library browser, you need to click on File, and then you'll have the option there. And fingers crossed, it's already logged me in, which is fine. And now we should have here the options to actually search and find known good or reference waveforms that we can pull down directly. So if we were looking at this particular vehicle, then this is a VW, and it is a transporter. So that's all I'm going to put in for the minute, and we can click search. And then we have all the options here. Now, if you know the engine code, you can also type that into here. We do know what fuel it is, which is another option. You can put that in as well. However, I think we've only pulled 13 options, I think. When you click on here, you can actually see in brackets a number, and that number represents how many waveforms are available for that model of vehicle. So if we scroll down, oh look, as luck would have it, a guy called Ben Martins has uploaded a waveform to the waveform library from a VW transporter. How nice of him. Now we can either just zoom in at this point and see. Interestingly, he's actually used voltage there instead of current, which is fine, we can do, but if we just wanted a straightforward cam crank signal, we've also got this here as well. There's plenty of options there for you guys. I think it would be good to get into the habit of using the waveform library almost as a cloud for all your own waveforms. So if you was to click Save As, you see the option down here to save and share, or just share. If you filled in all your details and got some notes on there as well, click Save and Share. You're connected to the internet. Why not? Then they're automatically uploaded. One for you to see whenever you need them. Also, heaven forbid, if your laptop breaks or you lose all your content or your own reference waveforms, they'll all still be there. So if you go to your waveform library, and again, this is where technology decides to trip you up, isn't it? There we go. See, at this point here, you've actually got my waveforms. So you can click on there, and anything that you've uploaded will automatically come up. And they're the ones that are for you. They're your own ones that you've uploaded. So these are ones that have been uploaded in the past. So they're always there for you. There we go. Good stuff. Okay, right. Now we're going to move to some additional techniques then, and some other options that we've got within PicoScope about how to actually do further analysis. So maybe if, for instance, you've got a vehicle with a slight misfire under load, so when it's idle only, there's no fault. Then the ways that we can actually bring more information out are things called mass channels. usually this strikes fear into everybody that I talk to about maths, and they panic. But don't be afraid, and in the words of Mr. Steve Smith, math channels are cool. Now, I don't remember maths being particularly cool at school, but actually there is an ongoing topic on the forum, and which will include some links into the chat. And obviously, if you need to find them, PicoAuto.com, go to the forum, and there is a link to useful links on there, and you'll be able to find the maths that's ongoing. Now, Steve's doing some great work there, and you can download these with the captures. One brilliant thing about maths channels, they can be applied post-capture. So nothing you can do with your original data is ever going to be hurt. It's all just going to stay there, and you can apply as many maths channels as you like to the captures, and they can be used to reveal much more information. Keep skipping forward a little bit. So one useful thing for this, we have a maths channel called Crankshaft within our software. If we think about how misfire detection works within an ECU, we're going to almost look at the same sort of thing, but using our maths channel. So misfire detection looks at the acceleration and deceleration of the piston during running. So as the piston travels up to a cylinder, there's resistance, obviously due to compression. So there is a natural slowdown in RPM or crank speed as this takes place. Now, once combustion has taken place, piston is forced back down the cylinder, and this results in an acceleration and an increase in RPM. So you can see here, so this would be where compression starts to take place. And then, actually, I don't know if that's, you can see that actually. Let's bring that up. There we go. So we should be able to have pistons now traveling back up the cylinder to compression. As it meets compression, RPM is at its lowest point. Combustion takes place. The now piston is traveling down the cylinder with an increase in speed. We can use our crank maths channel at this point to actually help us determine if there is a cylinder that's not performing as well as it should. So, just see if that's moved on. I'm just waiting for the internet to move to the next slide. Eventually. There we go. So how are we going to do this? We're going to use the crankshaft sensor to calculate our RPM. So let's move to do this setup. So what we're going to do is we're going to set up our scope now to look at capturing just the crankshaft sensor. And I'm also going to keep cylinder 1 as a reference. So I'm going to keep my injection current just so we've got a reference to where cylinder 1 is in relation to our crankshaft position sensor. So bear with me 1 second. Seamless, just like that. It's like we've rehearsed. Okay, so we now want to move back to PicoScope. Now, I don't really need any of this information still on the screen. So one way to get rid of it all is click the home button, and that will reload all your default settings back into the software. So you're presented with a nice clean screen again. It's a nice quick way if you're moving between jobs to get rid of the information. One thing to bear in mind though is that your channel labels will change. So channel A now for me is going to be plus or minus 20, but it's going to be my crankshaft position sensor. And channel B is going to be our current clamp again, as we're looking at cylinder 1. So we should have the option now to put in injector current, and just add a note in there to say that it's cylinder 1. Right, so we want to think about time again and how much time we want. We're probably not going to need a second per division at this point. Let's look at doing 500 milliseconds per division. Do you have the option here now? Maths channels do like a bit more of a higher sample rate. You'll probably see it when we do it, but I'm going to increase my sample rate to 5 million samples. So what that means is that I have basically more dots on the screen to play about with.
think about it as almost like a pixelated camera, if you like. So if we used to have 1 megapixel camera, if you try and zoom in on that capture, it's not as good as if we had, say, a 12 megapixel camera. It just gives you better detail when you're zooming in, but it also allows us for the mass channels to work a lot better. Okay, do you know what then, guys? I think what we'll do is we'll just start the engine and we will run and we will get some data on the screen and then we'll go from there. Hang on, got to put the fuse back in. It's got to start. Okay. Just let that go around again. Okay, Barney, that's lovely, thank you. The things here to bear in mind with mass channels, we need to make sure that we have a full screen of data in order to perform our mass channel on. If you don't have, what you'll end up with, and I'll show you it actually and see what it does, but you'll see that because there's no data there for actually us to do any maths on, it just goes a little bit haywire and goes a bit crazy. So we will demonstrate that. Okay, so we now have our data and we are wanting to set up our crank mass channel. Now, before we can do that, we need to actually determine how many teeth the crankshaft has. So we need to know how many points are on there for us to determine get our crank mass channel correct. To do this, we can zoom in. Now, interestingly, there are some, if we didn't know any better, we'd say, well, hang on, there's some weird gaps going on there. What is that about? Again, guys, this is where you may want to see, go to the waveform library and determine, is that the correct signal for this vehicle? We can do it. Let's have a look. So if we do the same again, just wait for the waveform library to kick into gear. There we go. Hopefully, guys, you should have noticed we've actually made a few improvements to the waveform library and how we connect to it. It seems to me anyway that it's a lot better, but in terms of connection and actually looking up waveforms. So hopefully you guys are seeing that as well. So again, we've gone VW and transporter. Click search. Says that now. Now it decides to play up on me. Okay, come on. Okay, here we go. Right. So we're gonna not look at that one. We want to find one with a cam crank signal. So again, here we go. So we can see on here that just by clicking on the image, it gives us a slightly exploded view, so almost like a zoomed in. So we can see here that actually between where we got the camshaft signal, we know that there's the small pulse and small pulse, so we have this repeating pattern. We can see actually that there is these 4 dropouts. As it is with this vehicle, there's 2 missing teeth, or there's 2 gaps on the crankshaft set at 180 degrees apart from each other. So we know that the signal that we're seeing is correct, so we're happy. Okay, so now, once we know that we're happy that that is a true signal, we can bring our rotation rulers out again. We can place them at 720 degrees, so 2 rotations of crankshaft. So we should see where the injection event's taken place. So there we go, that's our full 720. We can now split that up into 360. So this here is 1 revolution of the crankshaft. So I know that I need to measure, or I need to count how many teeth are in there. Now you could look this up on technical information. However, PicoScope actually you can do this a lot quicker. And we can do that using measurements. So pick a point. Now I'm going to pick this edge that's within the gap. We know that this gap should be present, and that's 180 degrees round, and then the following one is our full 360. So now what we can do is we can go to measurements, add a measurement. It's channel A that we want to measure on. The type of measurement I want to do is a falling edge count. It's going to count the number of times that that pattern falls and between the rulers. And we can click OK. So there we go, guys. Very, very quickly, nice and easy. It's counted 58 falling teeth. You could zoom in and count them all if you wanted to, but why do it when the software can do it for you? So typically, crankshaft sensors are either 60 minus 2, so we get the 58, or 36. They tend to be the common ones that we tend to see. But this makes sure that you are actually counting it correctly. So 58 minus 2. So we're going to use 60 as our number of teeth for this crankshaft sensor. Okay, so now onto the maths. So tools and maths channels. And this is the box that you are going to be presented with. Now, obviously, as we said, maths is cool, right? So obviously, I've got a lot of options here. These are based on my library and they stay with it. However, the built-in ones are already there for you. So you have these options straight away ready to go. However, we want to create. Enter the equation for this maths channel. We're going to click on Advanced. And here we have the option for crank. We click crank, it automatically puts it up in the box up here, but it's saying that the formula is invalid. To complete the rest of the formula, we need to tell it I want to perform a crank match channel on channel A and buy 60 teeth. That's it, guys. If there's more information, there's lots of information on our forum regarding match channels, and please feel free to have a little look. Obviously, going forward, we can try and answer some questions today as well, which isn't a problem. Okay, so crank on A60. You can change the color should you wish. I'm going to keep mine in black just because it looks quite clear on the white background. Place your name. This is already set up for you. Now the range. Be mindful of the fact that at the moment we're saying I want you to select a scale or select a range of 0 up to 9,000 RPM. Now this vehicle was only ever idling, so it's nowhere near that. So I'm going to change my range and I'm going to put that down to I'm going to put that down to 2,000 RPM. So that's where I want it to perform the maths. Okay, so now we have the option down here. It's come up as number 2 because I've actually already got one in here. That's from the rehearsal. So we can click the little tick box and then click OK. Okay, so there we have it. So to be fair now, guys, I'm not really interested in the data from channel A. So if you want to try and clear up your screen a little bit, we can right-click anywhere and use the channels. And then if you select A, it removes it from the screen. Right, let's zoom in a little bit then. So what is going on here? Now, as we said before, with how misfire detection works, it looks at the acceleration and deceleration of the crankshaft. This is exactly what our maths channel is showing us. It's showing us the speed, the rate of change of the crankshaft in relation to combustion and compression. So here we have cylinder 1. We have an increase or an acceleration as it slopes upwards. Actually, I'll tell you what, let's make this a little bit easier still. Let's bring the rotation rulers out again that we've been using and place on our injection events. Again, we can partition that up so that we know that here we have cylinder 1, using the firing order again, 3, 4, and 2, and then back to 1 again. So it's this repeating pattern. So if this is cylinder 1, acceleration, cylinder 2 is coming up here. So this is where we start to get a decrease in speed in the crankshaft. Combustion takes place, so we have an acceleration again. 1, 3, and then 4, 4. What's going on there? I've done that slightly wrong. should be there, guys. Sorry, this is my fault. There we go. So combustion has taken place. We have a peak speed here. Deceleration for cylinder 2. Acceleration. Sorry, let's get that right again. Cylinder 1, 3, and then 4, and then back to 2. So 3, 4, 2. Maybe I'll take the rulers out, it might make more sense. So here we have this drop in speed at this point. Now we already know that we've put a low compression on cylinder 4. So 1, 3, and then 4, there is no acceleration, there's no speed increase, and we get a big drop. And then we're back up to when cylinder 2 fires, and that's when we have this acceleration. So this, guys, is how we actually determine, or how the ECU looks to do misfire detection. Okay, let's just go back to our presentation quickly, because there's some further notes on that that might help us out a little bit. Okay, let's just wait for that to come on. Okay, so we have using the crankshaft sensor to calculate RPM. So we've set that up, we know that that's good. So things that we need in order for our crankshaft, our crank mass channel to work, we need to know the number, we need to have the crankshaft sensor signal, and we also need to know the number of teeth. And as we said before, that's quite easily done with using the measurements feature within PicoScope. Just hope that, there we go, so that's up on the screen now. So yep, so measurements, add measurement, which channel we want to measure on, what type of measurement. In our case, we used the falling edge count, and then between the rulers. You can use rising or falling edge. And just to recap on our crank maths channel again. So in order to create the maths, we select tools. Just waiting there, guys, just for that to move to the next screen. For some reason it's going backwards now, which is odd. Sorry about this, guys, please bear with us. There we go, so we should now see the maths channels on the screen. So yep, tools, and then we want to click maths channels and create. Obviously from before, I know we've done this live, then we've got the option to click crank, channel A, number of teeth, and then select the name and the range that we're on as well. So here we go, so here's a bit more of the results that we've got here. So I think this hopefully will make a little bit more sense when this comes up. Finally comes up, there we go. So this now, guys, should actually, this should make a bit more sense. So you can see where we have the acceleration in the crankshaft for cylinder 1, then that's for cylinder 3. Then we have the compression issue, or the reduced combustion effect on cylinder 4, which results in a decrease in speed. And then as cylinder 2 then actually picks up again, then we get this increase in crankshaft speed again. So you can see that pattern. Here you go, guys. So I'm sort of thinking, if we're going to use that in a particular situation, like I said, maybe this is when you've got a particular misfire under load, when you're not going to see this from a relative compression point of view, because we're only cranking at slow speeds, but this will actually help identify, and using the reference from cylinder 1, then we can actually put that in the firing order and determine the correct cylinder that's causing the issue. So, okay, so just again, just a quick recap, don't be afraid. You will not affect the raw data by applying maths. Maths channels can be applied post-capture. You do need to know the number of teeth if we're going to use the crank maths feature. And then obviously when we're looking at the range, just be reflective of where your RPM was when you did the test. And as we said before, there is the maths channel, maths or call, on the forum. A little tip there as well, guys. I mean, 9 times out of 10, one of the first things you'll do if you get a vehicle in the car is get a vehicle in the workshop with a fault is probably put your scan tool on. There's enough. We're not saying the scope is a replacement for your scan tool, but it's certainly there to help and confirm and verify the problem. So just remember, with misfire detection particularly, the ECU will look at the crank speed and determine which cylinder it is. So we're not doing anything really any different, but just verifying that that is what it's doing. So you have a look at PTCs first. They may help point you in the right direction, but then we can apply PicoScope to actually prove the fault. Okay, guys, so finally we're sort of getting near the end now. Just a little thing just to say about Pico technology, if you like. So just remember, the software is free. You can download it for free and play about with it, like I said. Technical support is free. So support@picotech.com. You can by all means email in. We'll help you out as best we can. The telephone hotline is free. Now, this it's not a hotline in the sense that it's like a premium call rate. It is just a telephone into our office here in St Neots. Technical information is free. Software updates is free as well. So any updates that we do to the software, it's automatically uploaded to the website, and you can download it for free as well. The forum is free as well, so as long as you signed in. And the Waveform library is free as well, providing that you have a PicoScope. So you do need to obviously buy a PicoScope to take a measurement. Okay, right guys, well, thanks very much for listening. It's been eventful and challenging at times, and I just hope, you know, that there's something in there that you can take away, and if there's something that you haven't seen before, and maybe, you know, even if you just pick 1 or 2 bits out of that where you think, yeah, okay, I can use that going forward, then it's all been worthwhile. So yeah, thanks very much, and thanks for bearing with us. This is the first time we've done it, and, you know, bearing in we'll see how the feedback goes, whether or not we do another one. But yeah, thanks very much. Thanks for listening. Okay. Brilliant. Okay, guys. Well, yeah, so, I mean, if we've got questions, we've got time. Obviously, we said this could be up to 2 hours. So fire away if we've got anything. I've got my handy crew here. Look, we'll just turn the camera slightly just to see if we can see the other guys here. There we are. Barney there himself.
Yeah,
and,
hi guys. If you want to fire any questions through the chat function there, then feel free. That would, otherwise, as we mentioned, just send an email to support@picotech.com. And yeah, we'd also love any feedback. I see some comments up there, which is really nice. Kind. And well,
thank you. I'd say I'm sweating, but I'm not going to broadcast that on camera.
Okay.
Yeah.
So, yeah, it looks like you guys are happy. So really appreciate your attendance, and we hope to prepare another one for you very soon. Oh, hello, we do have a question. Lovely, thanks. Okay.
Okay, cool. So what is the reason for locating cylinder 1 via the camshaft waveform versus ignition or injector? So what is the reason? So as I said before, in terms of relative compression, we're looking for a pattern. Now, if we want to do a relative compression test from PD, that's found that there's an anomaly within a cylinder, but we don't know which cylinder it is. So what we can do is try and find a relationship between the cylinder 1 injector. This is a diesel, obviously, so the injector is going to be the one we're looking for, and finding that relationship between the camshaft waveform. So let's just, I'm just going to see if I can bring one of these, one of our slides back up, so you can actually, the idea here. So if I put that one up, bear with me guys, let's just put this pan up. Okay, is this going to work? No. Okay, it's going to be easier to just go back. Sorry about this. Now, so we'll probably play havoc with the internet, but let's just see if we can get this get this slide up, because hopefully this will help with understanding why we're looking at cylinder 1. So
I'm just writing this up as well. Then.
yeah, perfect. So I think, guys, can we just check? Yeah, okay, so cool. We should have now this slide up with revealing the patterns. This is what we're looking for. We're looking for that relationship between the camshaft sensor and the and an idea of the injector for cylinder 1. It doesn't have to be cylinder 1, as we said. It could be 3, 4, or 2, whatever's easiest to get to, but it's associating that with the camshaft sensor. The camshaft sensor is obviously always going to pick up, regardless of whether the engine's running or if it's in a cranking condition. So from there, we can actually use that pattern that we've just got, then perform the relative compression test again with just the camshaft sensor, and then we'll be able to actually pick the pattern back up again in our relative compression capture. Oh, good. Does that make sense now? Brilliant. So yeah, so then we should have that idea that we can associate the position on the camshaft from where the injector's taken place and actually where our peak is in compression, so we can see the two together. So that's why we do it. So that's why it just helps. Obviously, we lose that injector signal when we're doing a relative compression test. Hope that helps.
I've just followed that up as well. Then.
Oh, brilliant. Thank you. Thank you. No? Okay, we got any more, guys? Did we pick out any more from there?
There was one about
1200 RPM. I'm on that one right now.
Okay.
Oh yeah, okay, great. So there's a Steve should be replying to Adam. I think you put a question about speed, engine speed. Steve is frantically typing away. I can hear the typing furiously on the keyboard with a response for you for that. So that'll be with you any second. No pressure, Steve, but everybody's waiting now.
And I've just typed it up in capitals as well, sorry. Let me start again.
Good. Good stuff. Okay, guys. Also, actually here, guys, if you have any possible topics that you'd like us to discuss going forward, and by all means, fire them in as well. If there's a particular subject, I mean, we've done relative compression and cylinder identification. If there is one on certain tests and techniques that might not make complete sense to you, that you think, do you know what, actually a little video like this might be helpful, then by all means put the recommendations in. We'll put them all together and we'll see if there's one in the future that we put together based around that subject. That would be great as well. Yeah, brilliant.
So we've noticed one about CAN bus testing now. We appreciate that. So,
CAN bus testing. Yeah. Okay, if somebody's fired in that, yeah, we'll put that together. To be fair, that is one that comes up quite a lot. So watch this space. Mass airflow. Martin, okay, that's I'll tell you what, it's probably going to be easier if I show you. So what we can do is this camera's still connected, isn't it? Yeah, brilliant. Let me just take it around. So bear with me on the jittery camera work here there, Martin. So if I bring it round. So we should have well, so there we go. So we should see there, Martin, we've taken a glow plug out. We've used one of our dummy glow plug adapters, but also put a compression hose in. Now what that does is it changes the volume of the cylinder and therefore reduces the compression ratio. So hence we have a low compression on that. So that's how we've managed to place a fault on that cylinder. So that's how we did it. Cool.
question you mentioned, 423 slower sample rates.
Good. 423 is fine.
423. If you've got that scope, it is fine for sample rate. It's particularly with Crankshaft, I know we discussed that. So if you are having, if you think you're to help improve your Crankshaft channel, for instance, like I said, I put my sample rate up to 5 million samples. To be fair, there's nothing wrong with sticking to 1 million samples. You'll still get a very similar result. But if you increase your sample rate, then it actually just helps. It helps the maths just a little bit more because you've obviously got more points for the maths to work on. In cylinder analysis, yeah, okay, cool. We'll put that on using WPS, yep, as a topic. That's great. This is all great stuff, guys. Thank you. It does obviously help us get a better idea of some of the problems that you guys are seeing and how we can use PicoScope to actually get to the bottom of these nasty faults that seem to be out there. All right. Yeah.
Last one was there, I think, for mass airflow. Was there another question for? Oh, that was Martin. How was the low compression?
Yeah. So we've used the video.
Yeah. How do we have a sample rate that's 2 casts?
No.
No.
For maths, not at all.
No.
No. Faster the better.
Yeah, definitely.
You're only limited in sample rate by channels and cycle duration.
Yeah.
That's
Number
it.
of active channels and the time
That's
across
it.
the screen.
Yeah. Hopefully you pick that up there, guys. But if we're saying about sample rate, the limitations are by the number of channels you've got, and or active channels, I should say, not the number of channels. But yeah, if you've got all four channels active, then the sample rate is obviously going to be affected by that. So hence why, when I did the crank maths on there, I've only used the 2 channels and plus a higher sample rate. It's absolutely fine.
I'm just backing that up with some text as well.
Okay. Oh, good stuff. Shall we? If I yeah, we'll just finish off them last few questions, then, guys. Just skip forward. It's professional, isn't it? Yeah. Excellent. You still in the middle of typing there, Steve?
One more sentence.
One more sentence. One more sentence. Okay, so I think we'll close it off then for today. And yep, thanks again. Thanks for all your feedback. It's really appreciated. And like I said, I do just hope, even if you got one little bit, maybe even it's like, oh, rotation rulers, didn't know they were there, then great. And it will really help with your diagnosis in the future. So
One more.
one more.
Yeah, this is just a clarity, because nobody can grasp all this in a quick sentence. So
No.
if they want more clarification, then I'll send it.
Yeah, absolutely. Yeah, guys, if there's anything that you wanted further information on, then like Barney said right at the very beginning, feel free to email in to support@picotech.com. If you used webinar in your title, then we'll get the email and we'll be back in touch and help clarify anything else that you might have.